All right, so that's web work problem number 6 that we'll start with, and we're going to use implicit differentiation to find y prime. So we take the derivative of each term. The derivative of 4 is 0. The derivative of 5x is just 5. I don't want to know. So we start here and take the derivative sine and get cosine of that same angle. So it's the cosine of xy squared. Now we have to go inside and take the derivative of that angle. And that's a product in there. So let's do the product rule.
2xy dy dx.
More. We've got a first and a second. I want first times the derivative of the second plus the second times the derivative of the first.
The second is 2xy dy dx.
Okay,
And then plus y squared.
plus y squared. There you go. Somehow we got to solve this for y squared. You can distribute this through here to solve for y. I'm sorry, not for y squared. We'll solve for dy dx. If you want to distribute, you can. I'm just going to divide it out. I'm going to divide by cosine of xy squared. And then just over here, I have 2xy dy dx plus that y squared. So let's move the y squared to the other side. And I've got 5 over the cosine of xy squared minus that y squared. And so just divide by the 2xy. So let's see. 5 over cosine of xy squared minus y squared. All of that will be divided by 2xy. What else you got? All right, you want to tell me what it is?
Yeah. It's at 2 in parentheses x squared plus y squared. And that's squared. And equals 25 parentheses x squared minus y squared.
No power on that?
No.
Okay. And the same instructions, we're going to find y prime. Okay, so there's power rule over here. Start up here. Bring this 2 down, multiply with that 2 and get 4. Raise this to 1 power less. So that's to the first power. Now you're going inside and take the derivative of each term. Derivative of x squared is here, plus the derivative of y squared. Okay with that? All right, these are 2 separate terms. If you want, you can think of that as 25x squared plus 25y squared, or minus 25y squared. So those parentheses can get out of our way. And now take the derivative of both of those. And I get 50x minus 50y y prime. So there's a y prime inside the parentheses over there. We need to get that out. And probably the best way to do that is just to multiply out the left-hand side. I'm going to take this all as one term and multiply by the 2x. And then I'm going to take all that and multiply it by the 2y y prime. And then we don't have the parentheses there anymore. So let's sneeze.
Oh, no. Yes.
Showing up. Gotta write bigger, huh? Nope, neither one. It's right in the middle. I just have to write bigger. Oops, don't do that. I want that one. I want that one. There we go. Okay, so I'll try to write bigger. So I'm going to take 2x times the 4, and that's going to give me an 8x. Then I've got the x squared plus y squared. Plus, now I'm going to take that times the 2y. So 4 times 2y is going to give me 8y. Then I have the y prime term, and then the one in the parentheses, the x squared plus y squared. Excuse me. And then the same step over here. Excuse me. Thank you, thank you. I'm afraid there might be one more in there. Okay, let's keep the y prime terms together, or let's get the y prime terms together. I'm going to keep this one on the left, and I'm going to add this to the other side. 50x is already over there, so I'm going to add this to the other side. So that gives me 8y y prime times the x squared plus y squared. And I'm adding 50y y prime, so plus 50y y prime. Over here I have the 50x. And I'm subtracting that first term, so minus 8x times x squared plus y squared. And we group those terms over there so that we could factor out the y prime. So I'm just going to do that with erasing. Put that y prime right there. This y prime comes out. And so we're going to divide both sides by what's in brackets. And our final answer then is y prime is equal to all of this, 50x minus 8x times x squared plus y squared. All of that over 8y times x squared plus y squared. Plus 50y. So what part gets you? Is it the derivative itself or the solving for y prime?
I didn't know about the factor, but I actually factored out. I fully factored it, probably messed up somewhere. Just like splitting it into 2 terms. That's a very nice trick.
Like, where?
Like when you did 8x x squared plus y squared and 8y y prime.
Oh, okay.
Splitting it like that instead of fully factoring it.
I don't know why, but do you like the y prime thing? Just,
Like where it's coming from or what?
well, no, I get it. It's just like another thing. I don't know. Yeah.
Same thing for me. Like
never like
it makes sense, but you just do it and get it wrong. Like I don't know why I'm getting it wrong.
I'd love to sit down and watch you work a few problems and that way I can catch you. I got these
It's sort of-
prods
it's
so that
sort
when you do something wrong, I can.
different shot color.
Yeah, yeah.
Okay, let's just go.
It works on dogs.
Have one. It's just for
The number one on homework, all the way down. 18.
I feel like I've done that.
Just
You probably have. Like if you took good enough notes in class, you didn't have to do homework. Yeah, you can just copy plus answer.
There's that. We've got taking good notes in class thing. Would you like to work some? Then I can watch you. Come up on the board and do a problem or two. Either one of you, I don't care.
which one?
Take your
Let me
pick.
check. Let me check.
You
which
can even
ones.
do one you know how to do.
My name's not that bad.
There you go. Had to put a little wrestling in it, so if the guy's ahead of you, you can tackle him.
Sure.
simple mathematics. Put this on the east board. All right. I can just pick it up and look if you don't want to do the web work. Got a whole book full of them.
Where's somebody have to motivate that? I just don't remember. I thought we were people talking about it.
You want to do it just random?
There you go. I got the, oh, yeah.
I think it was 15, actually.
15,
I
you're
remember the
jumping
problem.
way down toward the
It
end.
was-
All right,
it was
let's
X to the 5X.
do X to the 5x?
Yes.
I think so, actually. Or no, 6. Is it 6? Well, that's
It
fine.
doesn't matter.
Okay.
All right. So this is one of those with the base is an X and the exponent's an X. You're gonna start by taking the log of both sides.
Yes. Do that. Yeah, same as mine.
Yeah, I tell you.
You got it. That's okay. So Ln y equals 5x.
All right, now you can take the derivative.
Yeah, so it would be y prime over y equals, and we do that one. So it's 5x minus 1 over x. 5 ln x.
Okay. Solve for y prime.
Equals 5y plus 5y ln x.
Okay. And then if you want, you can take the y out and put in x to the 5x, or you can just leave it like that. I think WebWork takes it like that, or does it want strictly a function of x?
I think I had just been doing homework for like 4 hours at that point.
No, you can plug it in like that.
You can plug it in like that. That's fine with me.
And once you're white prime, like separate. The brains are together, yes.
That was perfect. Did I spell all that? You did a little simplifying here, and
Oh, did you take the?
you cancel the x here when you multiplied. So that's just 5, and then multiplied by that y, and then that 5y times the natural log of x.
I think I somehow got a Y on the right side. I don't know.
I don't know either.
Doing the one over x, cancel the x in both the right and the left. Oh, wait, never
There
mind,
is no
never
x
mind.
in the left, it's a y. And that's the y that's here.
Yeah, I was talking about the, yeah.
You guys need another? Yes. Easy for you to say. Do I need to Heimlich you? Took a first aid class in college. Would take it or would take it? All right. It doesn't accept the y, then let's factor the y out. We put it here. And then if you want to put this in where the y is, you should take it.
So if it doesn't take it just with the y, then you plug the original y back in.
Right. What's strictly a function of x. We don't know until you try. Sometimes it'll take it, sometimes it won't. I get these problems from different sources and the program differently. Any others in that web work? Anybody working on the next web work yet?
I'll work one.
Sure.
Number
You got one in particular?
Number 13.
Yeah, the Y.
I haven't tried this one yet, so
We won't throw things at your head.
this might be terrible.
You want to know terrible. I left the house in a rush and forgot my coffee. Would anybody like to go to my house and pick up my coffee for me?
Extra credit, I will.
For extra credit, I thought you would just do it just so I don't turn into a witch here in about 5 minutes.
I'll tell you what, I don't think one up to Starbucks.
Oh, that'd be heaven. That'd be heaven.
Whatever you want.
I saw a guy walking into the biology building with one of those Starbucks boxes of coffee. And I almost tackled him. I thought, that's what I want right there. The Mongo headache is on its way.
Parentheses sign?
Yeah.
Looks like it.
Inverse sign.
Yeah.
4x plus 3.
Is there another parentheses or no?
Chat here. Let's see what's on the chat. Can you zoom in on that, please? Uh-oh. I don't know how to zoom. I can only do left and right board.
Just tell me everything's right.
Yeah, right big. Yeah, I don't know how to do the zoom thingy. Increase the font.
4x minus 3?
No, plus 3.
Close parentheses, raised to the 8,
Yeah.
and then close all parentheses.
No, the 8's on the outside. Like,
Okay. So then this starting parentheses isn't here.
Yeah, that starting parentheses goes home to 8.
no, like this is a starting parentheses, and then
Oh.
then it goes to the end. Like,
Outside.
yeah.
Does that matter at all?
It doesn't matter quite a bit.
Yeah.
That means the
Otherwise it
inverse
would-
trig function is to the 8th power, as opposed to
Like,
the,
if you put it outside the parentheses outside of the 3.
after the 3, that means only the 4x plus 3 is to the 8th power.
Really? Maybe that's why I'm saying this wrong.
8. Should I? So this is where I always get tripped up. Do I need to open another parentheses?
You do.
Okay, and then it's.
General
No, it's the sign.
formula for the inverse sine of u is 1 over the square root of 1 minus u squared. Not to crack anywhere, we're gonna lose it. 1 minus the u squared. What is your u in this case?
You, it is
All right, so put 4x plus 3 right there.
right here.
Right there where your u is.
Use the other board and keep that.
Yeah. 1 minus 4x plus 3.
And that's the square root.
Now you're inside taking the derivative of 4x plus 3 before you close it.
Oh, before I close this.
Yep. You just put it in the top. Put it in the top of that fraction. And then,
Up here.
yeah. I was gonna try to save you some erasing, but you can erase.
Oh, sorry.
So
Is
you're
that-
inside,
And then do the inside.
inside right there,
So just 4x
just 4.
or 4. Yeah.
Little time symbol, so that that's 14. There you go. There you go. That make sense, everybody? Derivative of the outside brings the 8 law to the 7th, and then the derivative inside is the derivative of the inverse sine.
Is that it?
That's it, all done.
Awesome.
Once more.
The chain rule is easy because it's just a board.
Right.
It's super short. So I don't
You can't,
understand.
It's at the 8 inverse sine of the 4.
Someone needs to do research about doing homework on drones just so you get on the board.
Well,
That's why he's
I
doing
think
this
it's quite
one.
clear what, I think when I watch somebody do work, it looks better than just
So
sit there on paper.
this is the first derivative right here, which is all this. And then when you do the second one, when you open the next parentheses, all of that has to be in
Yep.
that parentheses. I always end up putting this one in another.
Well,
parentheses.
in this case, it wouldn't matter,
Oh, okay.
right? Because when you multiply three things together, it doesn't matter the order that you multiply. Anybody got next? It's like in the regular basketball court, comes the basketball, you can hop on. All right. Well, I want to see how your related rates are doing, so I'm gonna grab one out of the book. Get you refreshed on that. That one is that one.
I think the reason I was confused for 15 is because I tried to use that formula where it was like x or like u to the or a to the u equal the derivative of a to the u equals.
Yeah, but you can't do that when you don't have an A. You have a function of X. A stands for a constant, right? Single letter is a constant. You use the function of X. Okay, I'm gonna do number. Ooh, that says use the law of cosines. I'm not gonna do that. You don't remember the law of cosines. I think number 50 might be something that looks like one of your web works. This is section 3.7 on related rates, and this is out of your book, number 50. So I'll read it and then kind of write stuff down. It says, at noon on a certain day, a truck is 250 miles due east of a car. The truck is traveling west at a constant speed of 25 miles per hour, while the car is traveling north at 50 miles per hour. So I'm gonna make a picture. Put the truck 250 miles due east of a car. So let's see, the truck is east of the car. So here's the car. Here's the truck. At noon, that's 250 miles. And then you're told that the truck is traveling west at 25 miles per hour. I got to turn my truck around. Still looks backwards, doesn't it? Like that. Oh, goodness. There's his headlights. He's going this way, 25 miles per hour. Car's traveling north at 50 miles per hour. And we're supposed to find at what rate is the distance changing at time t. The distance between them. So we've got this kind of action going. One's going east, one's going west, one's going north. So we have a triangular shape which all three sides are changing. Draw it up here. This is the car. This is the truck. And this is the distance between them. All three things change.
Is this gonna be on test two, the mid range
Uh-huh.
problems?
Okay, so I want distances, and I think we're gonna write distances as a function of time t. I don't know how to do this without putting a t in there.
I think you're looking for a formula for T, like using.
I mean, then
FT.
it's, okay, won't be much implicit differentiation because I can write it in terms of t. Like, if this car goes 50 miles per hour for t hours, how far has it gone?
Yeah.
I don't think you're looking for an answer. I think you're looking for the
T.
formula.
That's what I'm gonna get.
The whole
So
formula.
I'm gonna label this as 50 times t. Does that make sense? This distance is rate times time. So there's rate times time. But we've got to use the 250 miles. If this is initially 250 miles, it's getting shorter by 25 miles per hour. So I'm going to write this as 250 minus 25t. And then the distance between them will just be the Pythagorean theorem, right? So I know, let's call this distance d. So we know that d squared is leg squared plus leg squared. So that's the distance squared between them. The distance has the square root,
Take the derivative.
but I don't want to take the square root with derivatives. So let's just call this f of t. We'll take the derivative of this. We can always put the square root back on, right? If we're going to take the derivative of the square root, that just gives us one extra term, and I don't want to mess with that. It's the stuff that's inside that's going to matter. So let's just call that f of t, and we're going to find, we don't need implicit differentiation. That's explicitly a function of t. So to get the rate that the distance between them is changing, oh, I can use it on this.
That's
How
literally
about we
just
do that?
distance formula.
Let's do that. Let me use a capital D on this, or this. And this will, I'll show you where I don't need the square root sign. Let's just take the derivative over there by writing that derivative as 2d times d prime. And then take the derivative over here, bring the 2 down, raise that to 1 power less. Multiply by the derivative inside to get a negative 25. Then do it again over here. Bring the 2 down, raise that to 1 power less, and multiply by the derivative of what's inside. And so when we solve this for d prime, I'm going to go ahead and put this with that and write a negative 50 here times 250 minus 25t. And I'm going to put I'm going to go ahead and multiply all three of these. 50 times 50 times 2, 5,000. So that's the rate in which the distance between them is changing at any time t. Right, because d prime here means the derivative of d with respect to t.
What happened to the? You're dividing by.
I'm dividing by, so it should be over here. Thank you.
That's just-
Swap boards. Swap boards, go west. There it is.
I think the hardest part for these is gonna be, like, I can get to the point where I'm drawing the illustration of what the question is saying, but then figuring out what equation to use and then know how to take the the appropriate part. That part I'm just.
See more.
That comes
I'm
from,
still
from practicing, right? The more you see a problem, they all kind of look alike after a while.
Is there gonna be like a,
If things are moving in the shape of a triangle, I think Pythagorean theorem,
Mhm.
unless they're discussing an angle of elevation, then I think in terms of trig. Okay, at what time is the distance between the car and the truck neither increasing nor decreasing? What does that
The
mean?
rating is 0. That change is 0.
B. At what time is the distance neither increasing or decreasing? In other words, the rate of change in D with respect to T is 0. So D prime is 0 when that numerator over there is 0. So let's set the numerator equals 0. Set this. Barely fit. That's a negative 50. Thank you. All right, so we're going to solve that for T. Do that right here. In my pictures. All right, so I'm going to multiply out negative 50 times 250. 5 times 25 is 125. So negative 12,500. And then negative 50 times a positive 25t, times a negative 25t is a positive. Again, 5 times 25 is 125. This time I have 1 0 there. And then I have plus 5,000t is equal to 0.
is that 12,500 T?
No, I
Or
don't think
plus?
so. There's no t here. The only t is in this term. Oh, and here. This one, yeah. 1250 has the t. So I'll add those two together and get 6250t. Move that to the other side. And then we're going to divide by 6250.
Another 0.
And that goes twice, right? It's like t is equal to 2.
Oh, it is. I wonder what's on this.
So what could that possibly mean, that the distance between them is neither increasing nor decreasing?
Is it they meet?
Is it
They meet together?
both of their rates are the same?
Hey, let's think how I'm going to explain that. I'm explaining that to you.
Both of their rates are,
It's just an instant in which the distance between them isn't changing. So it's not getting bigger and it's not getting smaller. I didn't do the dividing by 2. I said the only thing that makes this thing equal to 0 is if the top is 0. The bottom has no effect on whether it's 0 or not. Okay, so I didn't divide by 2. I just ignored that and set the top equal to 0. Well, think about what this is. This is describing, right? It's an equation of a circle, right? some equation of a circle. I've got a circle centered at an origin on the DT plane. And what does the derivative tell us in terms of the geometric facet of the, what's the derivative?
The rate.
Okay, but if I were just graphing D against T. So the tangent is horizontal here. So what happens when the tangent is horizontal? Well, the graph is either going to have a maximum on it or a minimum on it. Right? Well, I don't think we can look for a maximum distance between them because they're going to get farther and farther apart. So my bet is that in 2 hours, that's where the distance between them is going to be a minimum. Right?
But that doesn't mean they're necessarily mean.
No, it doesn't mean they're meeting at all. It just means that that's the smallest distance between the two of them. And I think that's the next question. What is the minimal distance between the car and the truck? All right, so at t is equal to 2, the distance between them is a min. And then you can find that distance by plugging that number into our distance formula. We can put t is equal to 2 up here. When t is 2, that's 50, so this is 200. When t is 2, that's 100. So the distance at that time is that. T is equal to 2, the distance is going to now be the square root of 100 squared plus 200 squared. That's whatever that is the minimum
Plugging
distance.
2 in,
2 in for the time, to give the
Verifies it.
actual lengths.
and that's the minimum.
That's the minimum. Is that what it is? It's not gonna be 300, it's gonna have a square root of 5 in it somewhere.
Did you plug in the original distance formula?
Well, I just did
Oh,
it
there's-
geometrically
Oh.
instead of going to formula. Let me do one that's not that particular. I've done all of them. All right, let's do this one. Again, I'll read it to you first. This is in the review exercises. It says on New Year's Eve, a ground level network TV camera is focusing on the descent of a lighted ball from the top of a building that is 600 feet away. The ball is falling at a rate of 20 feet per minute. At what rate is the angle of elevation of the camera's line of sight changing with respect to time when the ball is 800 feet above the ground? Number 77, on page 220. I'm gonna move the camera to the east side here. Okay, so here's the picture. We've got this lighted ball coming down. So there's the lighted ball. And it's coming down. Over here is a camera. And they gave us the distance that the camera is away from where it's coming down. The building is 600 feet away. The ball is falling at a rate of 20 feet per minute. So as that's coming down, the angle of elevation of the camera's line of sight is changing. So the angle of elevation goes from camera to ball right here. Let me give that a name. That angle of elevation has a rate of change. And that's what's being described next. We got to find that rate. At what rate? We got to find that rate. At the time when the ball is 800 feet above the ground. So I have to find that when the ball is 800 feet above the ground.
Build a triangle 600 as the base and the height is 800.
No, because that's changing. 600 is not changing, but the height is changing and the angle's changing, so we need to put variables there. Save that number for last. Okay, for things that are changing, put a variable. I already did one here, we're gonna do one here. A y, y sound okay with you? And then this 20 would be a dy dt. And that's going to be a value of y that we substitute in after we generate the related rates equation and take the derivative. But I don't need a variable for the 600 because that's fixed. So what equation would you like to start with? The equation that relates the theta and the y.
So that's gonna be a
Tangent, that's right. I got opposite and I got adjacent. So we're going to start with the tangent of theta is equal to the opposite over the adjacent. Now we're going to take the derivative of both sides. The derivative of the tangent is going to give us secant squared of theta. Theta is a function of time, so we tack on a d theta dt. What's the derivative on the right-hand side? All right, the 600, the here is a constant, so I pull it out, take the derivative of the y and get dy dt. Now we're going to solve for d theta dt. That means I should have numbers for everything else. I got a dy dt. I don't have anything to put in for the theta over here. Got this number, that's this. Coming down, I should even make it negative, huh? What am I going to do with this term? Well, we haven't used the 800. There's your clue. So let's stop the balloon, the ball, whatever thing is falling here. At some instant, this is 800. And this is 600. Did you know anything about theta or the secant of theta at that time?
well, secant is one of the close.
Might need the hypotenuse.
Yeah.
Would be 1,000?
Is this a 3, 4, 5 triangle? That's the question.
Yes.
This is 3 times 200. This is 4 times 200. So yes, indeed, this is a 3, 4, 5 triangle. This should be a 5 times 200. So yes.
My geometry teacher was the football coach, so can you explain the 3, 4, 5 stuff?
Oh, it's a Pythagorean theorem. This squared plus that squared is that squared.
But there's certain triangles that like are always going to be 3, 4, 5.
3 squared is 9. 4 squared is 16. That adds to 25.
Oh,
So it's called a Pythagorean triple.
There's other ones.
There's
what's the
that-
6?
There's a 5, 12, 13, 5, 12, 13 triangle, and then there's one that's got a 17. I don't remember that one.
So just looking at it, are you just seeing if they're factors of those?
Yeah, if not, just do the Pythagorean theorem and you'll get the 1,000 with a little effort. But anyway, if I know the hypotenuse is 1,000 and the adjacent side is 600, then I know what the secant is. Hypotenuse over adjacent. Right? So now I've got a number to put in everywhere. So that says that the secant of this angle is hypotenuse 1,000 over adjacent 600. I cancel there and get 10/6 or 5/3. So I'm going to put 5/3 into the secant of theta. Then I'm going to square it. So I have 5/3 squared. times d theta dt is equal to 1/600. dy dt was a -20.
You just put the value of secant in for all the secant things.
Are we just assuming the dy/dt is constant?
Yeah, it told us that. It's coming down at a constant rate of 20 feet per second. So that's 25/9 here. Let me simplify here. That's a -1/30. So if I want to get this to the other side, multiply by 9/25. 3 goes into this 10 times. 3 goes in this 3 times, so I've got my answer right there. The angle is changing at a rate of -3/250 radians per, what's my timing unit, minutes. D theta dt. And the -3/250 radians per minute. So as the ball's coming down, the angle gets smaller.
Do you use right-hand rule calculus, or do you just pick a direction?
What do you mean?
Like whichever direction, you know,
Yeah, but then we're not doing vectors, we're just doing, linear measurements.
I guess that makes sense, and it's just counterclockwise.
So -1/30 times 9/25.
Okay. 9 and 30 have a common factor of 3, so I canceled it.
Well, right, but I mean, how did you get the 9/25?
I've got 25/9 here, so I'm gonna divide by it. But to divide by a
okay,
fraction,
okay.
the same as multiplying by the reciprocal. Try this one. Suppose you have base of an isosceles triangle. It's growing at a rate of 2 units per hour. Right triangle. Yeah, let's make it an isosceles right triangle. Base of an isosceles right triangle is growing at a rate of 2 units per hour. How fast is the area increasing at the instant when base, that's a length, Switch to boards, switch to boards. I kind of wrote in no man's land there. The base of an isosceles right triangle is growing at a rate of 2 units per hour. How fast is the area increasing at the instant when the base has a length of 10 units?
What is it in isosceles right triangle?
So an isosceles, both legs are the same.
Yeah.
45, 45.
Both legs have the same length.
Is that, I thought that was just that definition of isosceles.
Yeah, but I made it a right triangle so that we can find the area real quick.
Wait, does that make it not isosceles? Oh, wait.
Oh.
This length is the same as that length.
Okay.
Right.
And
So
that
I
is-
just need, this is changing, but I don't need a different variable.
Cool.
Right. Yeah, this one's kind of easy because I made it an isosceles right triangle. So this says that dx dt is 2.
Area
Excuse me.
is 1/2.
So I've given you that dx dt is 2 at the instant when x is 10, and I want you to find dA dt. So where do you start?
A.
A is what?
It's 1/2 x squared.
1/2 x squared. That's the key about this thing being isosceles. In a right triangle, both legs are the same, so I didn't need 2 variables. So our governing equation over this whole problem is kind of a little simple formula. A is 1/2 base times height, but the base and the height are the same thing. So you start from there and take a derivative. Take the derivative over here and you get the dA dt. And the derivative over here, not just x, dx dt. X times dx dt.
X is changed.
Yeah. And then you put those 2 numbers in. X is 2, dx dt, oops, dx dt is 2, x is 10. So 10 times 2 will be 20 square units
Oh, wow.
per hour. Short and sweet, huh? All right, well, I guess until you try those, I don't need to work anymore. I'll go ahead and start the next section. The next section is section 2.8. We're going to talk about something called the differential. Back to the east. All right, so this is section 2.8. Point 8, 3.8. Go back to chapter 3.8. As soon as I wrote it. Actually, the differential is just part of the derivative. Let's look at a picture and I can point to it. I'm going to put a function on this graph. Kind of see. Oh, come on, Ken, work with me. As we look at a point on this graph, where'd that blue mark go? Bag of markers somewhere. Let's look at the tangent line to this function at some ordered pair x f of x. So that's the graph of y is equal to f of x. We'll draw the tangent line right here. And it's going to look like that.
Is this giving us like a somewhat of an introduction to differential equations kind of thing?
No,
It's not in there.
not at all. Not at all. If I move over a little bit, I'm moving over, say, delta x units. So I'm going to pretend that this is a small increment in x. So go up here and find this y value here. And that'd be the ordered pair. X plus delta x, and whatever the y is there, f of x plus delta x. The idea here is, what if this is a complicated function with a very messy rule? Trig functions, logarithms, exponentials, and I want to figure out this number roughly. Well, I could take this and plug it in. It's probably just too messy. I want to get a quick idea of what that number is. And so I say, well, why don't I just go by to the tangent line and find the number here and use that number to approximate this one. If these points are close enough together, so are those. Well, what's the equation of the tangent line to f at x? The derivative is the slope. And then there's my x1, y1, right? So I'd have y minus f of x is equal to f prime of x. And then I guess I should call that a f of a, but I should have called it a f of a. So evaluate this at x is equal to a. So that I'd have an x minus a here. Solve this for y. I'll put the f of a right here, plus f prime at a times x minus a. So even if this is a messy number, if I put it in here, all I got to do is subtract and then multiply by a number and add something. So my tangent line will have a nice quick approximation to what this y value is. We're going to use that part. This part of the equation is going to have a name. And let me put some other colors on here. Let's see. Let's see how the blue works. This length from here to here in blue
Here.
is the exact change in y. That exact change in y, we're going to denote delta y. So the length of this blue segment is called delta y. The jump between the tangent line point and that actual point, this length in green or not, that color. This green over. This length here in green is the jump in the tangent line to the graph, and that one's going to be called the differential in y, and denoted with dy.
Is that what the D is, differential?
So we're going to use two different approximations. In our picture, we're going to use that quantity dy, which is the differential in y. to approximate delta y, which is the exact change in y. dy is roughly equal to delta y. And dy is going to be the derivative of, look at this notation. We use this to denote this, right? That's the same dy. So if I treated this as if they were two differentials, the differential in y and the differential in x, and just solve for this, then I get dy is equal to f prime of x times dx. This is called the differential in x. The differential in x, since x is the independent variable, is exactly equal to the change in x. So we've got two different things going on here. I can approximate a change in a y value, and I can approximate a particular y value. If I just want to approximate this change, I take my derivative and I plug in my numbers that describe the change. If I want to approximate the value of the function at a particular point, I use the tangent line. This is what we call the linear approximation. And the book designates it as such. Replace the y with L for our linear approximation at any x is going to be the value of f at a nearby nice point plus the derivative at that nice point times our change in x. And that's what the x minus a is. Let me write it with change in x notation there. F of a plus f prime, this black marker is making me mad. F prime at a, x minus a is our delta x term. And so when I write it like that, there's our differential in y. Our linear approximation to a point on the graph of f is going to be equal to, or roughly equal to, the value of the tangent line at that particular point. So I need to swap over here to the west board here in a second and write that down. This picture is telling us two things. It tells me something I can write. That we can approximate a change in y as y changes from x is a to x is a plus delta x with dy is roughly equal to the exact change in y. Change in y is f of a plus delta x minus f of a. Messy calculation. This is a simple calculation. Or we can also estimate the value of a function at some messy x-coordinate. The messy x-coordinate is a plus delta x using the linear approximation offered by the tangent line. We just construct the tangent line at the nearby point, f of a plus f prime at a times x minus a. And then we substitute in the nice value. Or the messy value we can put right there. This part here is the delta x. Ugh, that's way down. What is wrong with my board? Go up. Oh, there's that one. There we go. I want it right there. That doesn't scroll. So let me give you a quick for instance. If you're going to approximate, say, the square root of 9.03, you'd say, oh, that's roughly equal to the square root of 9. Okay, so you approximated the square root of 9.03 with just the square root of 9. This says we can do better. It's the square root of 9-ish. And that ish is going to be the value of the derivative times the delta x. So we get closer to our approximation. So here's my example. Use the linear approximation to estimate, what did I say, the square root of 9.3? So if this were the graph of the square root function, we're going to write the equation of the tangent line to that graph at x is 9. And then we're going to plug in the 9.3 to see what the value is on the tangent line. And it's going to estimate the value of the square root of 9.3. So let's do this in general. Let's take away the numbers and let's define f of x to be the square root of x. We're going to write the equation of the tangent line to f at x is 9. So let's take the derivative. That's x to the 1/2. So the derivative is 1/2 x to the negative 1/2, which is 1/2 times the square root of x. We're going to plug the 9 in there to get the slope. F prime at 9 is 1/2 times the square root of 9. So that's 1/6. Okay, so we use y minus y1 is equal to m times x minus x1. So y minus, well, what is y1? What's the y1 value here? 3. It's equal to m times x minus x1. x1 was 9. And so this thing, when I solve it for y, add the 3 here, is the equation of our tangent line. That's the thing we're calling the linear approximation at any x. So there's the f of a. A was the 9, plus f prime of a times x minus a. So now we're going to put the messy x in there. We're going to put the 9.3 in for x. So, run out of boardroom. Nope, wrong way. One more. There's a little bit of space right there. So the linear approximation at 9.3 is this 3 plus 1/6, 9.3 minus 9. So that's 3 plus 1/6 of 0.3. Let me write 0.3 is 3/10. And then the 3 cancels into the 6. Twice, so I get 3 plus 1/20. And 1/20 is 0.05. So that's saying the square root of 9.3 is roughly equal to 3.05.
What's it actually?
I don't know.
.0495.
Okay, good for you, huh? Two decimal place accuracy. This, though, approximates the change in Y. So suppose that you have some sort of business and you can figure out the cost of making, you have some data that'll help you calculate the cost of making X items. And then maybe, so you're making 1,000 items now, you know how much that costs. And somebody says, well, what if we change our production and make, 1,080 items? How much more will that cost me? Well, you can figure out the cost of 1,080 items, subtract the cost of 1,000 items, and that's the exact change in cost. But again, what if cost is a messy function? The idea is we can approximate that change in cost by finding the slope times the change in X. That's what dy is. We can find the derivative of our cost function at those 80 items or at the production level of 1,000, and then multiply by our increment in production in X. So I'll do an example of that next time. So that's what we'll do on Monday. And I think next week is our week before our test. So I think about whatever week, this might be the last section that will be on the test, but we'll still cover stuff beyond next week. So get busy and get caught up, get working on those.
When's our next test?
I think it's the 20th.
Yes.
Yeah, thank you. Thank y'all. Have a good weekend. Getting you guys out.